Welcome back to the course on audio signal processing for music applications. Until now, we have been presenting different techniques for analyzing and synthesizing sounds. It's time to put that in practice and to make use of it in actual music applications. So this week we'll be talking about sound transformations, about how to transform the representations we have been talking about and then resynthesize a sound that is a modified version of the input sound. We will be talking in this first theory lecture about the short time Fourier transform and about two types of manipulations or transformations, filtering and morphing. And also we will be talking about the sinusoidal model and how we can use it for frequency scaling and time scaling a particular sound. Let's start with the short time Fourier transform. This is the block diagram that we saw, in which frame by frame we are selecting a fragment of a sound, windowing it, computing the spectrum, obtaining a magnitude and phase. And now what we are introducing is a transformation block after this spectral analysis. From this transformation, we obtain a new magnitude and phase spectrum that can be inverted, and we can obtain a new sound that is a modified version of the input sound. Let's first talk about filtering. We talked about filtering in this course before, and the idea is that filtering can be implemented in the time domain using convolution, or in the frequency domain using multiplication. So this is what we are using here, the short time Fourier transform for, applying the filtering in the spectrum by multiplying the magnitude and phase spectrum of the input sound with the magnitude and phase spectrum of the filter. Strictly speaking, what we are doing is if we have the magnitude and phase separate, we're going to be summing the phase spectra and multiplying the magnitude spectra. Okay, so the filter is expressed by its frequency response that has a magnitude and a phase, and the phases are added and the magnitudes are multiplied. Okay, and the equation below shows this idea. So the complex spectrum of the output is equal to the product of the two magnitude spectrum, of the magnitude spectrum of the filter with one frame of the magnitude spectrum of the input sound, and the phases are sum, but again is the whole phase spectrum of the filter with one frame of the input sound. And then we can perform the inverse FFT and obtain an output sound. So let's see that in practice. So here we have on top left a fragment of an orchestral sound, a very short fragment, of which we compute the magnitude and phase spectrum. So below that we have the red line is the magnitude spectrum, and below is the phase spectrum. And then we have the magnitude spectrum of a filter. Okay, a filter can be zero phase, so it's normally the important aspect of the filter is the magnitude of it, and in many situations we basically can discard the phase because it has no effect. So in here what we're going to do is multiplying the magnitude spectrum of the filter with the magnitude spectrum of the input sound. However, since we are in a log scale in dB, we add the two together. So we'll be adding these two shapes that we see here. And the shape on the right is the added result of these two shapes. So it's a modified version of the input spectrum. Okay, and the phases basically are untouched. And then we obtain the output sound Y by performing the inverse FFT of that. Let's actually see these for a complete sound. So on top we see the spectrogram of the complete orchestral sound. We have heard before, but let's listen to it again. Okay, And now in the middle we have the shape of the filter that we are applying, the magnitude of it, okay? And then what we are doing is multiplying this shape, but every single one of the frames of the input sound in the magnitude spectrum. And we obtain the spectrogram below. So let's listen this resulting sound. Clearly much softer because we have attenuated most of the frequencies. We have only let pass, so this is a band pass filter, the frequencies around 1,000 and something hertz, and the rest are very much attenuated. Okay, and these ones we have even boosted them a little bit, but of course energy wise we have reduced the energy quite a bit. Let's now use the short time Fourier transform for another type of transformation, what we call morphing. In morphing, we start from a sound x1, in which what we're doing is basically the short time Fourier transform analysis resynthesis, and at every frame we are multiplying its magnitude spectrum by a magnitude spectrum of another sound that is also changing in time. Okay, so what we're doing is we're taking another sound x2, we are doing a similar short time Fourier transform process, and at every frame, so basically it's a parallel process, we are only using its magnitude spectrum, and then what we're doing is smoothing it, because the idea is that we are applying the general shape of x2 into x1. Okay? And if we see the equation below, basically what we're doing is similar to the concept of filtering, but now the x2 is time varying, so it has an L, it has a frame, and we're multiplying these two magnitude spectrum of x2 and x1 at frame L, and the phase spectrum is only the one of x1. So let's see that in practice. This again is the same sound that we played before, the orchestral sound, and below it is again the magnitude and phase spectrum. But now what we are doing is this black line is a smooth magnitude spectrum of another sound, but this one will keep changing the same way that keep changing the orchestral sound, and we'll be adding these two spectra again because it's in a logarithmic scale, and we will be creating a new set of spectra from which we do the inverse FFT. Let's do this for the time varying sound. So on top we have the orchestra, we already have heard about it, and let's now listen to the other sound, the X2 sound, which is this pitch male sound.
Do you hear me? They don't lie at all.
And the spectrogram we see in the middle is the smooth version of this X2 sound. So it does not have the detail of X2, it just has the general shape. And these are the two spectrograms that we are summing frame by frame to obtain the lower spectrogram, MY, okay, in which we are definitely seeing that is not X, and it's not X2, it's a modified version of the two. Let's listen to this modified version.
Do you hear me? They don't lie at all.
Okay, so it clearly has aspects of the orchestra, and basically we can understand the speech because the general shape of the magnitude spectrogram is the one of the speech. Maybe one way of understanding this sound is as if the orchestra was playing through the vocal track of this male, and therefore reproducing the phonetic kind of textures of the speech sound. Okay, now let's go to the sinusoidal model that we already have seen. So we have again the analysis of the sinusoidal model with the peak detection and sinusoidal tracking, and now what we're going to be doing is modifying the resulting sinusoidal values. But there is a small change here. We are not going to take the phase values. The phase values are very sensitive, and if we want to make any transformations, it's very difficult to take care of them. So what we're doing is regenerating the phase values from the frequency values. So we'll be modifying amplitude and frequencies, and then we will be generating the phase values after the transformations, and this is the input for the synthesis, and is the same synthesis that we have been doing until now. These are the particular operations we are doing on the output of the sinusoidal analysis. So the new frequencies and new amplitudes are the result of applying some scaling factor, SF, to the input frequency, and also the reading of the input frequencies are controlled by some scaling time factor, which allows us to move inside the kind of input array, input signal, so that we can slow down or speed up the reading of the sound. And we do that for both amplitude and frequency. The amplitude, since is done in the dB scale, we sum the scaling amplitude factor with the amplitude of the input signal. Okay. And the phasers are regenerated. They are not from the original sound, and they're generated by starting from the previous phase, and therefore we need an initial phase at the beginning, which can be 0 or can be a random value. And then at every frame we add the frequency, the new frequency that we are generating, so that the phase is automatically unwrapped and generated from the frequency values. So this would be, for example, a scaling envelope. So the scaling factor applied to a particular sound, and therefore it would be an envelope in which we'll read from the input time. So the horizontal axis is the input time, and it will assign an output time to every input time. So changing the reading position of the input time and modifying its length. So let's see a particular example of this time scaling effect, in which we start from a Madranga sound, okay, and we are analyzing that with the sinusoidal model. So on the spectrogram top, what we're seeing is the original signal and the synthesized, the trajectories of the sinusoids. And let's listen to the sound first. Okay, and then below it is the transform spectrogram, both the transform sinusoids, so these are the modified sinusoids in which we have spaced them differently, so we have been reading them at a different speed. And if you look at the horizontal axis, the time axis is very different. So the original sound was 2 seconds long, and now this output sound is basically 3 seconds long. So it has stretched by a factor of 1.5. Okay, so what we are seeing here is the output sound, but of course with a new time information. So in terms of frames, there are many more frames because the length of the frame will remain the same. So let's listen to the resynthesized modified sound. Okay, so we have changed the duration, not in a constant scale. In fact, we basically made all the onsets at the same sort of distance. Okay, so we basically wrapped the time information in a way to generate the times in a different position and making the sound a little bit longer. Of course, the number of possibilities here is enormous, and we can just play around with this mapping in any way we want. And in terms of the other transformation, the frequency scaling applied to the sinusoids, well, we also need a scaling envelope in which it's time varying. And so here we have the horizontal axis time, and the vertical axis is the scaling factor. So that means basically that at beginning of time we are multiplying all the frequencies of the sinusoids by 0.8, and by the end of the sound we're multiplying all the frequencies by 1.2. So the frequency will start lower and end up higher. So let's see that in a particular sound. So this is the orchestral sound that we have already heard, and we see here the sinusoidal analysis of it, the spectrogram, where we see the original spectrogram and the sinusoidal tracks, and then below it is the transform sinusoids from that curve that we just showed. So here we see that at the very beginning the sinusoids are more compact, so they're lower frequencies, and at the end they are higher because we have multiplied them by 1.2. So let's listen to this modified orchestral sound. Okay, of course it doesn't sound natural because this is not something that you normally would do, and there is some distortions, but it can be refined and obtain some good results by applying this type of techniques. There is not much information about the details of how to apply these type of transformations on sounds, but if you look in Wikipedia you can have some pointers and some initial references for sound effects, equalization, and how to apply time scaling and pitch modifications to sounds. That's all I wanted to say in this first theory lecture. So we have gone over some particular transformations using the short time Fourier transform and the sinusoidal model. And then in the next theory lecture we will continue with the other models we have presented and using them in some other type of transformations. So I hope to see you next lecture. Bye bye.